Okay, good morning. So this is going to be a course on supersymmetry, elementary to start with, at least first 10-15 lectures, where we'll construct methods of how to write supersymmetric field theories, and be followed by real stuff by Srihari when he'll make contacts with LHC physics for supersymmetry. Anyway, let me start by listing a few books and articles from where I have drawn most of the material I have in my notes. And the books are: one, Baer and Xerxes Tata. It's a book called Weak Scale Supersymmetry. There's another book by Dries, Manuel Dries, Rohini Godbole, and Prabeel Roy. And the book is called Theory and Phenomenology of S particles. There's a book by Peter West, Introduction to Supersymmetry. And Supergravity. And there's a book by Julian Wess and Bagger. Bagger is with 2 G's or 1 G's? 2 G's, I think. And it's called Supersymmetry and Supergravity. Many years ago, there was a school organized by University Grants Commission where I had lectured. So there's an article which has been published in a book now called Supersymmetry and Supergravity. It's a book edited by Bala Iyer and others. There's an article, an old article by Salam and Stradzzi. And it's called Supersymmetry and Superfields. There's also a review, more phenomenological, by Karina and Haber, and it's called Higgs Boson Theory and Phenomenology. There's another review by Keith Olive, it's called Introduction SUSY, Astrophysical and Phenomenological. constraints. And that should give you a feeling, at least the titles, that how far supersymmetry goes. Astrophysics, particle physics, phenomenology, standard model, beyond standard model, and string theory, which is not mentioned here. I will not talk about why supersymmetry. And for that, last year I gave a talk somewhere in Bangalore, and I have picked up copies of my lectures. People who are interested in a few of them, they're not, I don't think everybody will get it here. There are only 10 copies, but you can share amongst yourselves. So now let's get started with what I'm going to do. First, I'll try to remind you about things that you already know. That is some group theory. Everybody knows how to write, how to describe rotations in classical mechanics. And rotation in classical mechanics, if I call a space 3 vector x, y, z, I'll also label them as x1, x2, x3. Then rotation acts on these coordinates in a way that rotates the coordinates xl through a matrix RL K xk, where R is a 3 cross 3 orthogonal matrix. Orthogonal means R transpose R is a unit matrix. That's how rotation acts on the coordinates. And they have determinant 1, and they form a group. So R form a group. And name of that group is SO3. And these R contain 3 parameters. Call them theta 1, theta 2, theta 3, or together as a threesome, theta L, which are the angles of rotation in the 3 planes in 3 dimensions. So this measures rotation in x2, x3 plane. So you make a rotation around x is x1 in the x2, x3 plane or yz plane, and this is along the x-axis. This is measures rotation along x3, in x3, x1 plane, and this one x1, x2 plane. Now that was how rotation acts on space coordinates. In quantum mechanics, rotation act on states as unitary operators and let's give them a name, u of theta. Theta is the collective name for these three parameters of rotation, theta 1, theta 2, theta 3. So a state psi under rotation becomes a state psi prime, which is u theta times the original state. And u theta is a unitary matrix, 3 cross 3 unitary matrix, which is parameterized as exponential I times these three thetas times JLs, where JLs with L 1, 2, 3 are the generators. These are generators. These are Hermitian. The JL Hermitian conjugate is JL. So 3 Hermitian generators exponentiated and multiplied by theta makes the unitary transformation. And unitary means u dagger u times u dagger is a unit operator. That's how rotation acts in quantum mechanics. Now, what are these generators J? JL are made up of regular orbital angular momentum, let me call it Lm, plus spinning. This is orbital momentum let me write an expression of Lm is x, Lm is half epsilon m n k L n k, where L n k are x n p k minus x k p n. The space, momentum, space, momentum. That's the angular momentum. And the momentum on the space of coordinates as a differential operator representation, and that is Pn is minus I d by dx n, or we'll write it like this. So this is I minus xn dk minus xk dn. There's an exercise, if you have not done it earlier, I think most of you would have done it. Check that these L satisfy the algebra. Lm, Ln commutator is an I times epsilon m n k L k. What this epsilon here and here is a completely antisymmetric symbol. It changes signs if you interchange any of the two. Is 0 if any of the two are equal. And 1, 2, 3 is plus 1. Now, these unitary operators also form a group. U thetas form a group, and the name for that group is SU2. And the general SU2 algebra generators of SU2 satisfy the algebra JL JM is I epsilon M N K J K. This is the algebra of SU. This is the SU2 Lie algebra. Sometimes people want to make a distinction between the group SU2 and Lie algebra of SU2 by writing SU2 small as compared to as against this capital. This is U, not O. So sometimes people write it as this way to make a distinction between that's the name of the algebra and this is the name of the group. An important property of these is that these three angles theta 1, theta 2, theta 3 have finite range. Angles theta 1, theta 2, theta 3 have finite range. And that's elementary, is that think of one of them, theta 1 in the x2 plane, x2, x3 plane. So theta 1 is a major rotation. So if I take a vector here and make a rotation by some small amount, follow it by another rotation, follow it by another rotation, follow it by another rotation, another rotation, follow it by another rotation, and finally I can reach back to the position that I started from. So by successive transformations, rotations, when the total angle of rotation becomes 2 pi, I get back to my original position. So that is the finite range. So each of the theta i's ranges from 0 to 2 pi. Next, what I want to remind you of is representations of SU2. SU2 algebra. Or SU2 group. Now, as you will recall, representations of a group are given in terms of representations are given in terms of the eigenvalues of Casimir operators. Now, Casimir operators of SU2 are two. Define J to be sum of the product of all the J's. So J1 square plus J2 square plus J3 square. This object, call it J square, has the property that it commutes with all J's. So Casimir operators are the operators that you construct from the generators in a way that they commute with all generators. That's the definition of a Casimir operator. So it is the eigenvalues of this j square that specify the representations of SU2, and eigenvalues of j square are given in terms of small j times j plus 1, where j takes values 0, half, 1, 3 by 2, and so on and so forth, integers and half integers. So that's how representations of SU2 are classified in terms of the eigenvalues of the quadratic Casimir, j square, which is simply j1 square plus j2 square plus j3 square. And a representation for a given value of small j is specified a given representation j, the name for this j is spin, is specified by another label m, which takes values from minus j plus 1, minus j plus 2, so on and so forth, plus up to j minus 1 and j. So a representation is made of a certain component of fields, certain number of components, and those components are labeled by another label m, which takes values from minus j to plus j with an interval of 1 unit. And you could write where this m is the eigenvalue of any one of the three generators j1, j2, j3 on that state. Any one, and for some convenience or some habit token, I think we take it to be j3. That is, if I a representation j with its components specified by label m, when j3 acts on that, has the eigenvalue m. And this is an eigenstate of j square also, and to j square jm eigenvalues are. Now let's look at some simple examples of these representations. Simple examples. The first one is the trivial one, when j is 0. Small j is 0. Small j is 0. So get 0, small j is 0, and if small j is 0, m is 0 by the rule that we specified. So this is a one component representation, a one-dimensional representation, because it has only one component, one-dimensional representation. Sometimes also called singlet. And the generator j in this representation, j square has eigenvalue 0, j3 has eigenvalue 0. So j is 0, j's are 0. So rotation leaves this unaffected. So it's a singlet of rotation. Rotation does not transform it at all. So that was a trivial representation. The non-trivial, first non-trivial representation is when J is half. And it is two-dimensional. Simple enough, we said by the rule here, M has to take values minus J up to plus J for half with an interval of 1. For half, J equal to half, the possible values of M are plus half and minus half. So what you have is the state half M is made up of two components. Dimension of singlet was 1, dimension of half just by simple counting is 2. So that's what he said, because it can have only two components by the rules that we have specified. What are the generators? The three generators JL in this representation. The generators of this representation are sigma L by 2, where sigmas are polymatric. Sigma 1 is 0, 1, 1. Sigma 2 is 0, minus 1, plus 1. And sigma 3 is 1, 0, 0, minus 1. I. Right? Convince yourself that sigma JL defined by this satisfy the algebra we wrote here. So that is the second, but first non-trivial representation. Second next representation is when J is equal to 1. This is a three-component representation. Let me write it. 1 M. M has values plus 1, 1 and 0 and minus 1. So that's the three components. So dimension of J equal to 1 representation is 3. And what are the generators in this representation? Generators would be three generators, L equal to 1, 2, 3, J1, J2, J3. And since the three-dimensional representation, there will have to be 3 cross 3 matrices. And those 3 cross 3 matrices are JL with its components IJ. Each one of them runs from 1 to 3. The 3 cross 3 matrix is equal to minus I epsilon Lij. This I is square root of minus 1 and this I is labeled, please. Bad notation. Is that clear? This I is square root of minus 1 and this I is the label 1 which takes values 1, 2, 3. Check for yourself that these 3 cross 3 cross 3 matrices satisfy the algebra Now we said that earlier, but let me repeat. The most general representation now is general representation of spin j is Jm with components Jm, Jm minus 1, Jm minus 2, so forth, and J minus m plus 1, J minus m. And in all, the number of components is 2j plus 1. That's the dimension of spin j representation, 2j plus 1. For spin 0, it's one dimensional, spin half, it's two dimensional, for spin 3, it's three dimensional, and so on and so forth. And for a general representation, JLs are 2j plus 1 cross 2j plus 1 Hermitian matrices. Now, if I take two representations of SU2 and take a product, that's also a representation of SU2. Product of two representations of spin J1 and J2 representation is also a representation of SU2. But it's a reducible representation, irreducible. And what do we mean by reducible? Is a product of two representations. I'm using this symbol now from this. I'm not labeling the M, keeping the label M, because that's a little too cumbersome to do. So I take spin J1 representation, take a product with spin J2 representation, and this I can write as sum of irreducible representations. J1, J2 difference mod plus J1, J2 difference plus the last one is sum of J1 plus J2. And these representations are in the list that we made here. They are the irreducible representations of SU2. In particular, let me take a simple example, and this whole discussion was just to get that simple example. Think of a representation spin half example and multiply it by another spin half representation. This representation, this is a two-dimensional representation, this is a two-dimensional representation. So this has two components, this is two components. This together has 2 cross 2, 4 components. 4 independent components. These 4 independent components will break into irreducible forms corresponding to a singlet and a spin 1 representation. Spin 1 has 3 components, spin 0 has 1 component. So that's how the product of 2 spin half representations breaks into irreducible representation of a singlet and a triplet. Spin 0, spin 1. We'll use this elementary rule in constructing. In fact, we will not use too much of more than what this elementary rule in constructing supersymmetry finally. Next example, let's say half cross spin 1. So it's spin half representation times spin 1 representation. By the rules we have prescribed, this is 2-dimensional, this is 3-dimensional. So 2 times 3 is 6. So this whole representation is made of 6 components. And 6 components will break into irreducible representations of SU2 in the form of half plus 3 by 2. Is that clear? And so on and so forth. I mean, you can construct more examples. So like I said, this is 2-dimensional, this is 3-dimensional, this is 2, this is 3, and this is 2, this is 4. Dimensions. 2-dimensional, 3-dimensional, 2 dimensions, 4-dimensional. So that was a quick summary of what we already know about a rotation group. Next, what I want to remind you is properties of Lorentz group. There's only one duster here. So Lorentz group. So Lorentz group has this rotation group in addition to 3 rotations, 3 space rotations. It includes 3 boost transformations of special theory of relativity. Whereas these 3 space rotations we know are the ordinary rotations in the 3 space planes, x1, x2, xy, yz, and zx. The 3 boosts are transformations in 3 planes, tx, ty, and tz. One time direction and one space direction. So if on 4 vector x mu, Lorentz transformations act as, I'll just write now, not write mu. This is a collective name for the 4 x's, x0, x1, x2, or t, x, y, z goes to this. is a sum transformation matrix U, a 4 cross 4 matrix acting on X. That's how it acts on the 4 space-time coordinates. We'll specify what we use, how to write it, U. And on fields, let me consider some generic field phi of X. It acts as phi of X goes to phi prime of X. Phi of X goes to some phi prime. And we are looking at the same point X. Then it's some operator U. Let me, as a function of theta, the transformation parameters of the group times phi of U inverse on X. This is important. This structure is important to remember, that on the fields, phi of X goes to phi prime of same X as some operator U theta of phi and U inverse of X. Is everybody familiar with this little step? And what is U? U of theta can be written in terms of generators of this group. Exponential minus I by 2 theta mu nu m mu nu. M mu nu's are antisymmetric in mu nu. Four cross 4 antisymmetric matrix has 6 independent components. So there are 6 generators here. 3 corresponding rotation and 3 corresponding to 3 boosts. So there are 6 generators here. Theta mu nu are the parameters of transformations. And theta mu nu is also a 4 cross 4 antisymmetric matrix. So you have 6 transformation parameters and 6 generators. In SU2, these generators were Hermitian, but here they need not be Hermitian. In fact, some of them are not, and we'll see how that emerges. So though I wrote U here, U is not necessarily unitary. Now, what is the algebra? Anyway, there's a name for this group. Name for the group, generate the group of these transformations. Name of the group of U theta is SO3, 1. That's just a name. Another name is SL2C. What is the algebra of the generators? Algebra of SO3, 1 generators is M mu nu commutator M alpha beta minus I eta mu, first one and first one here, m nu beta. Take the first index here, take the first index eta here, take the second one, and then antisymmetrize pairwise. So minus eta mu beta m nu alpha minus nu alpha m mu beta plus nu beta m mu alpha. Or if you want to write it in a more compact notation and remember it, raise these alpha beta up through raising a lowering operator matrix. One zero 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 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. That's our choice of the metric. Raise and lower these alpha betas through this metric, multiply by I, then square bracket is antisymmetrize this pair, antisymmetrize this pair. Another quick way of remembering this relation. So that describes the Lorentz group and its generators. What we are interested in understanding the representations of Lorentz group. To do that, we'll have to do a little bit of redefining of these generators. Renaming of these generators. So rename. Take Mij. Ij's are 1, 2, 3 without the time label. And call that epsilon ijk jk. So M12 is J3, M23 is J1, M31 is J2. That's just renaming. And M0I, which is same as minus Mi0, call that minus Ki. So these are generators of ordinary space rotations, and these are the three boosts, the three boost generators. What happens to this algebra that we wrote, a general algebra, in terms of these renamed generators? Check using this Ji Jj commutator is I epsilon ijk jk. This I again is the root of minus 1, and whereas this I is the label, takes values 1, 2, 3. Is it in dummy index, is an index. So Ji Jj's go. That's precisely what was the commutation rule for rotations that we prescribed earlier. So this is what they satisfy. What about Ji with Kj? So Ji's commutated with Ki is I times epsilon ij kk. So this only tells you that Ji's, Kj's is a 3 vector under these rotations, and these J's rotate them amongst themselves. And then next, Ki, Kj is minus I epsilon jk, jk. Important to note, the commutator of two Ki's is not a Ki but a Ji. Commutator of two boosts is a rotation. But commutator of two rotations is a rotation. So the algebra of rotation closes amongst themselves. So Ji's form a closed subalgebra of this big algebra. So Ji's are generators of a subgroup of Lorentz group. So rotations make a subgroup of Lorentz group. Ki's don't make a group, because Ki, Kj commutator, this algebra does not close. It gives you a J. Now we also said here that the general element of transformation is written in terms of exponential I by 2 theta mu nu m mu nu. The thetas are the transformation parameters. So let's rewrite them also. Write theta ij to be minus epsilon ij k alpha k. And theta 0 I as phi I. Then what happens to u theta? U theta, which was exponential, let me break it into components. Theta ij, mij minus I, theta 0 I, m0 I. Half here, half goes away here because there are two of these. 0 I and I0 are same up to a sign, so they add up. And right now, theta ij, mij as minus epsilon ij k alpha k mij. Epsilon ij k mij k is jk minus twice alpha k jk. So it's alpha k jk phi k. Now signs right. Signs I have done wrong, because why? This is a minus here, this should be plus, and this should be plus, because this was defined with a minus sign here. So the general Lorentz transformation in terms of these renamed generators, where we have separated the rotation part and the boost part, can be written like this in terms of three parameters here, alpha k's, and 3 parameters here, phi k's. So that is an intermediate step. There's one more step we need to take before we try to understand the representations of Lorentz group. And that step is define another combinations of generators. Take Mi as a sum of half Ji plus I Ki. Now this I is again, so let me call it L, and NL to be half JL minus I KL. So this is another renaming. I mean, take a linear combination of a rotation I times a boost and rotation minus I times a boost. Take these two combinations. What happens to this algebra in terms of these new objects M and N that we have written? Very nice properties they have is that if you rewrite that algebra, verify that ML, Mn is epsilon L N K M K, NL N N is I times epsilon N K N K, and ML N N is 0. Exercise. Check this is so. It's a straightforward exercise. Use these and check this is it. But what does it do? It has a very nice property. What it has done is the original generators of Lorentz group have broken into two sets corresponding M's and N's, 3 M's and 3 N's. And their algebra is such that it closes. M's close amongst themselves, N's close amongst themselves, and M and N don't talk to each other. And each of these is the algebra of an SU2. So, Lorentz, algebra of Lorentz generators breaks into two SU2 algebras. Two SU2 algebras don't talk to each other, but yet they are not completely independent. Why? Because if I do a complex conjugation, they go into each other. So, under complex conjugation, SU do, well, under complex conjugation, M and NL interchange, and so the two SU2s interchange. So this is a very nice property, and this is a property we'll exploit in terms of writing the representations of Lorentz group, because we know how to write representations of SU2. Now, before I go down to representations, one remark. Lorentz group is not a compact group. Is non-compact. What do we mean by that? The rotation subgroup is compact. A rotation subgroup generated by JLs is compact. That we have seen earlier, and the reason it's compact is that, again, by successive transformations, when the rotation angle gets to 2 pi, I get back to the starting point. So the range of the transformation parameters is finite, which is all the alpha L's go from 0 to 2 pi. Alpha L's were what we had named as the parameters associated with the rotation. But boosts can be of any size, which means phi L's have a range from 0 to infinity. You can make a boost of any size. So that's what makes it non-compact. So this is compact. Now there is a general result that non-compact groups do not have any finite dimensional unitary representations, any non-trivial, finite dimensional representations, finite dimensional unitary representations. And in nature, we are interested in finite dimensional representations because we want to describe objects with a certain finite number of components. We don't want to describe things with infinite number of components because then there is no information there. So physical states have to be finite dimensional. So finite dimensional representations of the Lorentz group that we will construct now will not be unitary. The generators will not be Hermitian. Transformations will not be unitary. Now, so the finite dimensional representations of Lorentz group. And how do we generate the representations of group is we first figure it out what are the quadratic Casimirs which commute with all the generators. So the quadratic Casimir operators are m square, which is ml, m1 square plus m2 square plus m3 square, for the simple reason what we have learned earlier, because each m's and n satisfy SU2 algebra. And square of m1 square plus sum of m1 square plus m2 square plus n3 square will commute with all m's. Similarly for n. So in order to classify finite dimensional representations, what we do is that we have to give eigenvalues of m square and n square. So representations classified by their eigenvalues. Let's call the eigenvalues of m square to be j into j plus 1 and n square to be j prime plus 1. Because they are two SU2 algebras, so the eigenvalues will be where now j is 0, half, 1 and j prime also takes values in the same set. There's a little exercise you must do, and you must realize that I have been a little quick. When I discussed SU2 earlier, it was made up of Hermitian generators. It was a real SU2. And when I did representation of SU2, that SU2, I developed this theory of classification. But here, the generators m's and n's are not real, they are not Hermitian. But I am yet borrowing SU2. Convince yourself that for finite dimensional representations, the representations of this SU2, whose generators are not real, are not Hermitian, are the same as the representations of real SU2. Okay, so we'll go ahead with this. So we'll now label these representations by specifying values of eigenvalues of m square and eigenvalues of n square, where they are given by j into j plus 1 and j prime into j prime plus 1. So by two sets of half integers. I am not writing the m numbers for them. Each one of them will have m components. So I am suppressing that information just to shorten my notation. So you label the representations of Lorentz group by specifying two half integers, which are the values of j and j prime. Dimension of such a representation, from SU2 we learned that the dimension of a spin j representation is 2j plus 1. So we have 2j plus 1 times 2j prime plus 1. That's the dimension of the representation. So now let's write down a few examples. First one is the trivial representation. Lorentz scalar or a Lorentz singlet is j value 0, j prime value 0. And it's one dimensional, the singlet. The first non-trivial representation is you take the first J1 value to be half and J prime value to be 0. And dimension of this representation, this is two dimensional, this is one dimensional, 2 times 1 is 2, is a two dimensional representation. A name for such a representation is they are called spinorial or spinor representations. What are the generators of this representation? Now, generators of this first SU2 we had called them ML, which was half JL plus I KL. And SU2 spin half representation we have already specified is given by 3 polymatrices. And this generator NL, since under the second SU2 this representation is a singlet, did I miss an I somewhere? Yes. Good. The polymatrix is Hermitian, so that's it. Huh? But that's it. This one is Hermitian. It's not generically anti-Hermitian. ML, that's what we will see structure. In fact, it's a point I'm going to make. Trying to make the point next. It need not be Hermitian. See now. Now we'll see that what's happening here. Now this is because this SU2, this has to be Hermitian because that's what the representation of SU2 is, made of Hermitian generators. So this will be this. This is this. What does this imply? JL is equal to sigma L by 2 and KL is equal to, now I'll have an I here in KL and that's what the answer is. Now is plus I or minus I? We check it. What is it? I think minus I. Yes, minus will make it sigma L, sigma L. Now JLs are Hermitian, KLs are not. But that's what KLs are the boosts. JLs are the rotation, and rotation is the same as ordinary rotation, space-time rotation. JLs are the generators of rotation. Is that clear? So, if I make a group element exponential I alpha L J L, which is same as exponential I alpha L sigma L by 2. This is unitary. But exponential, another element phi L K L, which is exponential phi L sigma L by 2 up to a sign. Now sign is plus or minus, is not unitary. Is that okay? and that's because JL is Hermitian, KL is anti-Hermitian. Now there is a conjugate representation. Which is 0 under first SU2, spin half under second SU2. Generators here are ML half JL plus IKL equal to 0 and NL half JL minus KL equal to sigma L by 2. That tells me JL is sigma L by 2 and KL is I sigma L by 2. Notice JL here and JL for this representation are the same. So under rotation, both these representations transform the same way. And same way is like spin half representations, rotation spin half. But are different under boost, but not under boost. What are the physical objects corresponding to these representations? Physical fields or states. Half zero are left-handed fermions and 0 half are right-handed fermions. So these were examples of two-dimensional representations. There are two non-trivial examples, each other, they're conjugate of each other. Conjugate of each other is because under conjugation half zero conjugation is same as 0 half. They go into each other. Under conjugation, they go into each other. So the next example that we'll take up will be a 4-dimensional representation. A 4-dimensional spinner. These were 2-dimensional spinner representations, which is not an irreducible representation. These are irreducible representations. This is a reducible representation. And this is given by the sum of these two representations. Sum of the representation is also a representation. But it's not a irreducible representation clearly, because I can write it in terms of two split representations. This one is two-dimensional, this one is two-dimensional. 2 plus 2 is 4. A Dirac fermion lives in this representation. Dirac fermion is made of 4 complex numbers, which you can break into 2 left-handed components and 2 right-handed components, and that's what this is. This was third example. Fourth, another 4-dimensional representation. A real 4-dimensional representation. Spin half corresponding to first SU2 and spin half corresponding to second SU2. This has dimension 2, this has dimension 2, total dimension 4. And in this, it's convenient to write the generators in M form, M mu that we wrote earlier. It's more convenient to write them in this form. So I'll write down the generators in this form. Generators. M mu nu, there are 6 of them with components. These are 4 cross 4. Each one of them 4 cross 4 matrix because it's a 4-dimensional representation. Is minus I delta mu alpha eta nu. Antisymmetrize these indices beta. So the Lorentz group X through generators of this kind on this representation, 4-component representation. 4 space-time coordinates x beta correspond to this representation. So do momentum p beta. Any 4 vector is this representation, vector representation, 4-dimensional representation, irreducible representation. Here is an example of where 2 cross 2 is not same as 2 plus 2, because this representation is not same as this representation. This is a irreducible is made up of 2 irreducible representations. This is an irreducible representation on its own. This is why the Dirac fermion lives. This is why space-time vectors live. I think next discussion is to discuss Poincare group and representation of Poincare group, but I think I'm running out of time. Well, I have 5 minutes, but it will take me more than 5 minutes. So I think I'll do that next time. Any quick questions? This is all you know. So this was a revision. Next lecture will also be a revision, and then I think we'll start with real supersymmetry. And you will use some of these facts to construct supersymmetric algebra.